Hello class, this is Dr. Anderson and we are going to keep talking about those kidneys. We have talked about an overview of the kidneys, functions of the kidneys. We've talked about clearance, how you derive clearance, glomerular filtration, how you regulate glomerular filtration, lots and lots of wonderful things. And now we are going to discuss renal secretion reabsorption. And we'll see how it goes as to whether I make this one presentation or two, but here we go. All right. The proximal tubule is the first part of the tubules. It is the workhorse. It does a majority of the reabsorption and the secretion that the nephron does. It performs 2/3 of sodium and water reabsorption. What in the heck does that mean? That means that if your glomerular filtration rate were at 100, 66 mils of saline would be reabsorbed by the proximal tubule. Then you'd have 34 mils per minute going on to the loop of Henle. All of your glucose transporters and your amino acid transporters are found in the proximal tubule, so they accomplish all of that reabsorption. So by the time the filtrate leaves the proximal tubule, it should not have any glucose and it should not have any amino acids left in it. And of course, that is being driven by sodium reabsorption, and water will follow osmotically. Most of the drug secretion is going on in the proximal tubule. I'm not going to say other parts of the tubule don't secrete drugs, they do, but a great deal of it is accomplished in that proximal tubule. And we're going to be doing some hydrogen secretion, and if you recall our discussions from last week, the majority of that is going to be accomplished by secondary active transport using a sodium gradient. So that proximal tubule is just doing all kinds of wonderful things. This is a picture from Vanders Human Physiology, and this is basically a cell model for the proximal convoluted tubule, which I've abbreviated PCT, proximal convoluted tubule. So here we are in the lumen, and in the lumen we have a lot of sodium. On the basolateral side of the cell, we have our sodium-potassium ATP, and so we are using ATP to pump out the sodium. As we do that, as we pump out the sodium, we create a gradient for sodium to come in along its gradient. So here's the deal. We have sodium out in the tubule. It follows a gradient that was created by the sodium-potassium ATPase. And now we have a particle here that used to be out here. So that means the local osmolarity in the interstitial fluid increases. That means particle concentration is higher in the interstitium and water concentration is higher in the lumen. And what is osmosis? Osmosis is the diffusion of water through a semi-permeable membrane along a water concentration gradient. So water enters the cells. Now notice it can go through the cell. So here's water crossing the luminal side of the membrane. Here's water crossing the basolateral side of the membrane. What is going to be required here for this? Well, we're going to have aquaporins. So aquaporins are abundantly found in these cells, which allows water to then diffuse by osmosis through the cell. It's going to enter the interstitium, and because the Starling's forces in the peritubular capillaries favor reabsorption, then that water is going to enter the capillaries. Notice though, we also have some transport here. We have water going between the cells through the tight junction. So in the proximal tubule, the tight junctions are not all that tight. And all sorts of things can go in between the cells. So when we're going through the cells, That is called transcellular transport. And when we're going between the cells, that is called paracellular transport. But let me emphasize that whenever a particle is added to the interstitium, then water is going to follow osmotically. That's going to return the osmolarity back to 300 or whatever it was, probably 300, and return this osmolarity to what it was. So if water is always following particles, then the concentration of the filtrate doesn't change appreciably. So if we start at 300 milliosmolar in Bowman's capsule, by the time we leave the proximal tubule, we should still be at 300 milliosmolar. The composition will be very different. You know, we won't have glucose left, and we won't have amino acids left, and we'll have some acid, and we'll have some drugs. The composition will be different, but the concentration should be the same, and therefore the proximal tubule is characterized by something we call isosmotic reabsorption. So here's some more fun pictures. Here we are. Here's the basolateral side of the cell, and what I don't have drawn in my picture is a little old capillary. So here's a peritubular capillary out in the interstitium. We are using ATP to pump out a sodium ion and to pump in a potassium ion. This creates a sodium gradient. This sodium gradient is then utilized by, and I want to say this is actually two sodiums that bind to this transporter. This is the SGLT transporter. This is a secondary active transporter that uses a sodium gradient to drag along glucose. So then we cause a glucose gradient to be made, and then that glucose can leave along a concentration gradient by a GLUT transporter. Then glucose can easily go into the peritubular capillary and be returned to the general circulation. Now I have another cell and I have a similar thing going on, only now it's an amino acid. So we use our ATPase to pump out the sodium. We create a sodium gradient. So sodium then can come into the cell along its gradient, drag along an amino acid, and there are classes of transporters for classes of amino acid. We create an amino acid gradient, and then the amino acid can leave by facilitated diffusion. There are sometimes other kinds of transporters for amino acids, but for our purposes this is plenty of detail. Now, that amino acid then is going to go in the blood and be returned to the general circulation. So, what else is happening? Well, we have aquaporins that are going to allow us to bring in some water. Water is going to follow the sodium and glucose that's entering, and here's another aquaporin that will allow us to transport some water. Because as sodium and glucose are adding, the osmolarity goes up, right? So the osms go up locally, water follows, and then we return to 300 milliosmolar. So as we're moving along the tubule, let's see if I get my thing, as we're moving along the tubule, we're removing the water, we're removing the sodium, we're removing the glucose, we're removing the amino acids, and guess what? Things like chloride build up, things like calcium build up. Let's see if I can write that. Calcium, magnesium, I need my 2+. Phosphate, I'll just do a little thing right there. Phosphate, which is negatively charged. So all kinds of, or it's a phosphate ion is going to have 3 little charges on it. So all of these things start to build up. And what can they do? Oh, they can sneak through the tight junctions. Water can come this way too. So there's a fair amount of paracellular transport. Oh, you know what? I forgot one. Potassium. Potassium is reabsorbed. Now there are also going to be some leak channels for potassium. It's going to allow potassium to come in. Potassium will leak out. We turn around and pump the potassium back in. Alrighty? So, the big theme in the proximal tubule is a sodium-potassium ATPase creating a sodium gradient. We use the sodium gradient to make other gradients to transport other substances. And then a number of things, lots of ions. Another thing that can get dragged along is urea. Urea is slightly reabsorbed. So as urea gets more concentrated, there's a gradient for it to leave, and there's some facilitated diffusion transporters for urea, and urea can sneak in between the cells. So all kinds of things can be reabsorbed. Now this is the picture from your textbook Vanders, showing a similar thing. So here is our sodium-potassium ATPase. We're breaking up ATP and using the energy to pump out sodium. We're using that sodium to create a sodium gradient, and then sodium can drive the transport of other things, like substance X is brought into the cell, and then X can leave by facilitated diffusion. So X could be glucose, X could be an amino acid. Notice here's our hydrogen transporter. Sodium comes in along its gradient, hydrogen is pumped out against its gradient. We also see potassium leak channels. So there are potassium leak channels here. There'll be more potassium leak channels here. I wonder if I can draw a leak channel the way Vanders does. Yeah, sure she can. So potassium can come in this way too. Oh, rats, no. Potassium's not going to come in this way. Potassium's going to go out that way. But potassium could then come this way. Oh man, do I start this presentation over again or just admit that I made a boo-boo? Okay, so potassium could come in through the tight junctions, as well as calcium, as well as magnesium, as well as phosphate. There, I'll draw the whole thing, phosphate. Alrighty. Now, in addition to hydrogen being secreted, other things are secreted like drugs. So there are all kinds of transporters for toxins like uric acid or that kind of thing, or creatinine, that kind of thing. And drugs can use those same transporters. All right. So I showed you in the previous slide hydrogen going out in exchange for sodium, that the sodium gradient was created by this ATPase. But did you notice that I didn't show you how hydrogen got into the cell in the first place? Do you see a hydrogen ion transporter over here? Look over here while I draw my little peritubular capillary. Do you see a hydrogen transporter over here? I don't see one either. What the heck is going on? Well, in the filtrate, we're going to find a lot of bicarbonate. That bicarbonate is going to find hydrogen ion that we've secreted. And we're going to form something called carbonic acid. And guess what? Proximal tubule cells have an enzyme on their surface that's called carbonic anhydrase. Carbonic anhydrase then gets us a water and a CO2. CO2 can diffuse right through the cell. Water is going to come through an aquaporin. So now we have water and CO2. Guess what? carbonic anhydrase is in the cell too. Carbonic anhydrase then allows us to make a carbonic acid. Carbonic acid is a weak acid. It dissociates into a hydrogen ion and a bicarb. The hydrogen ion is then pumped out. So we keep cycling this hydrogen ion. How in the world does that ever change the pH if we just bring it in and bring it out and bring it in and bring it out? Well, look what we're doing. Over here, we're going to have a transporter, and it's basically a facilitated diffusion transporter. And it allows bicarb to leave. How can bicarb to leave? Because we're creating bicarb in the cell. Bicarb is higher inside the cell than outside the cell, and we allow bicarb to leave, and bicarb is then going to go in the peritubular capillaries and be returned. So gaining a bicarb is just like losing a hydrogen ion. Now, you may say to yourself, if I were queen of the universe, or sorry guys, if I were king of the universe, I wouldn't have something this complicated. Oh, dear students, just give me a chance here. This is such a beautiful mechanism because it lends itself well to acid-base balance. What happens if you have alkalosis and you have boatloads of bicarb? You know what will happen? You will not reabsorb all of it. So with alkalosis, bicarb is going to go out in the urine. That is such a helpful thing. What if you have acidosis? Well, my goodness, you are going to upregulate these transporters and you're going to get rid of every little hydrogen ion you possibly can. And while you're doing that, you're reabsorbing every little bicarbonate you possibly can. And as you secrete hydrogen ion and reabsorb bicarbonate, you are able to address the acidosis. So whenever you're mad at Mother Nature saying, why is it this complicated, you have to say, we must be getting something for that complexity. And we are. We're getting flexibility in the face of different pH abnormalities. So lots and lots of things are secreted. One of the students came up to me and was talking about this, and if you have acid in your urine, acid can change how things are secreted and absorbed. So for example, we have an anion here, and maybe we want to get rid of that. It combines with a hydrogen and maybe becomes lipid soluble and can come back in the cell. And we may or may not want that. Or we could secrete something. Notice we're secreting ammonia. There's a way to deaminate amino acids and make ammonia. That ammonia finds a hydrogen ion, makes ammonium ion. Ammonium ion is then trapped. So this ionic substance can go out in the urine. So hydrogen ion, an acidic urine, helps us get rid of ammonia. Other things might return being reabsorbed by diffusion, and it depends on what it is. Physicians can try to make the urine acidic or try to make the urine basic to help people with drug overdoses. So let's say we didn't want this anion. You could give somebody a lot of base, keep this anion in it, and it would promote it going out in the urine. So pharmacology and acid-base balance have a wonderful intersection here. And I will keep it there. If you have questions, we can talk about this more in class. All right, so we just left the distal convoluted tubule. we have reabsorbed a whole bunch of sodium and water. We have reabsorbed all the glucose, all the amino acids. We've taken up some potassium and some chloride and calcium and magnesium and phosphate and all these wonderful things. And every time we have reabsorbed a particle, water has come along. So all through the proximal tubule, we've been performing something called isosmotic reabsorption. Well, friends, we are entering the loop of Henle, and those bets are off. We are not doing anything isoosmotic at this point. And this happens in all the loops of Henle, but is particularly impactful in those long loops of Henle in those juxtamedullary nephrons. So, what's going on in the loop of Henle? Well, it has a descending limb, and the descending limb have aquaporins, and therefore the descending limb is highly permeable to water. But there are not transporters for electrolytes. So sodium and chloride, etc., cannot be reabsorbed in the descending limb because there are no proteins to do that. If you allow water to leave, but leave the electrolytes behind, then the filtrate becomes more concentrated as it flows deeper into the medulla. Why is that? Well, remember, in the medulla we have a highly concentrated interstitium that will accept that water along a concentration gradient. As we go up the ascending limb, oh my goodness, we have a completely different situation. The tubule is permeable to electrolytes because there are transporters, but there are no aquaporins, so it is impermeable to water. So as you pull out electrolytes and leave the water behind, the filtrate becomes less concentrated as you flow back towards the cortex. So I have a picture of that. In my descending limb of the loop of Henle, I have little spaces here which kind of represent my aquaporins. I really should have an aquaporin on this side of the cell and an aquaporin on this side of the cell, but it's not exactly working that way. Now, let's say it's 300 milliosmolar out here, and as we enter the medulla, it becomes 400 and 600 and 800 and 1,000 and 1,200 milliosms. Well, you have 300 milliosmol filtrate surrounded by 400 milliosmolar interstitium, and water will leave by osmosis, making the inside 400. And now you have 400 milliosmolar surrounded by 600 milliosmolar interstitium, and water will leave by osmosis and become 600. And now you have 600 milliosmolar surrounded by 800 milliosmolar, and water will leave, becoming 800. Are you seeing a pattern here? Now you have 800 milliosmolar surrounded by 1,000 milliosmolar, and water leaves by osmosis, and the inside becomes 1,000. And now you have 1,000 surrounded by 1,200, and water leaves, making the inside 1,200. So we're removing water on the way down and leaving the salts behind. On the way up, we have transporters that transport sodium and chloride, and then we introduce a loop transporter that reabsorbs sodium chloride and potassium chloride. So as the ions are removed and whatever water is left behind, and we pump out more sodium and chloride, but the water is left behind, then by the time we leave, the osmolarity may be around 100 milliosmolar. We've actually become hypotonic. So as the filtrate flows along the descending limb, it becomes more and more and more concentrated as you remove the water. Then as you flow up the ascending limb, it becomes more and more dilute as you remove the electrolytes and leave the water behind. So you came in about 300, you're 1200 maximally at the tip of the loop of Henle, and then when you leave you're about 100. So you actually overcompensate or become hypoosmotic. Now what's going on in the descending limb? Well, looky here. Notice we got a membrane potential. These cells have kind of a nice membrane potential, so a membrane potential across. Why? Because we have sodium potassium ATPases, and we have leak channels, and we have chloride channels and potassium channels. So of course they have a membrane potential. We are not doing anything with action potentials. We don't have voltage gated channels, but we're using these potentials for transport. Okay, great. So we're in the ascending limb of the loop of Henle. Looky here, sodium potassium ATPs. We're pumping in potassium. We're pumping out sodium. We're creating a gradient. Potassium can leak out. Chloride can leak out. We also have some potassium chloride transporters. So essentially what's happening is we're using this primary active transporter to create a sodium gradient. And then sodium drives the transport of 3 other ions, 2 chlorides and a potassium. That potassium leaks out, comes back in. So we have a little cycling thing going on here with potassium, which is kind of fun. But we're pumping out sodium. Sodium's driving 3 other ions, and so essentially sodium, chloride, and potassium end up getting transported across this cell layer. We also have some sodium-hydrogen exchange here. Maybe not like what we have in the proximal tubule. And we have some paracellular transport. This thing right here, this secondary active transporter, is called the loop transporter. It's the transporter in the loop. Why should everybody know about this? Because it is blocked by a drug called furosemide. And another name for furosemide is Lasix. And Lasix is a diuretic. It's a loop diuretic. So when furosemide blocks this channel, or I'm sorry, this transporter, then we have sodium, we have potassium, and we have chloride in the filtrate. We don't have sodium, potassium, and chloride over here. So we have ions going out in the urine instead of being concentrated in the interstitium. And as a result, water is less likely to be reabsorbed, which is why this drug is a diuretic. Notice that we're going to lose potassium in the urine, and therefore Lasix is considered to be a potassium-losing diuretic. And so some patients who need Lasix for their blood pressure or for their heart failure may also need to take a potassium pill so that they maintain an appropriate potassium level. So this, well, maybe I'll just go back 2 slides. So we're reabsorbing water on one side. We're reabsorbing sodium and chloride and potassium on the other side, and that sets up a gradient in the interstitium. And because we absorb all these ions from these long loops of Henle, the medulla is hyperosmotic. Now notice I don't say hypertonic, hyperosmotic. It's about 700 milliosmolar sodium chloride. But the other is about 700 urea. Why is that important? Urea can enter a lot of cells. So urea helps keep the medulla concentrated without shrinking the heck out of all of the cells. And I'll go back. So these cells also have urea in them, because urea is a penetrating particle. Little red blood cells over here in my peritubular capillaries have urea in them. And that means the cells are going to shrink a little bit, but not nearly the way they would if all of the interstitium were non-penetrating particles. So, not all of you went through the penetrating, non-penetrating particle business of osmosis last semester. I'm going to leave it there, but we can talk about it in more detail in class if you're struggling with this concept. All right. So, how does this stay hyperosmotic? Well, it's maintained by a countercurrent mechanism. What do you need for a countercurrent? You need a U-shaped tube, you need a means of exchange, and you need a gradient. So that essentially water is going to go one way and salt's going to go the other way. So if we're flowing this way, sodium is going to go and be dragged down into the interstitium, and water is going to go this way and be carried away. Now, PhD dissertations are made up of this countercurrent mechanism, and I just don't want to go there. What I want you to realize is that because you have differential transport characteristics on either side of the loop of Henle, you've got a gradient. And because you've got a gradient and a countercurrent, you've got a concentrated medulla. In addition, you've got a vasa recta that can recirculate sodium and water. So this is a drawing of the vasa recta, if I neglected to say that earlier, that can keep the salts in the medulla. So I think of the loop of Henle transports the electrolytes, the vasa recta keeps them there. So then we set up this concentrated medulla. And then, if we need to save water, we've got a gradient ready to go, and we can use ADH. ADH then will bind to the collecting duct and promote water reabsorption to save water when we need it. So in some courses, you may have gone into a lot of detail about the countercurrent, and I'm just not going to do that, because I think the countercurrent is more basic science relevant than clinically relevant. And so this is what I want you to appreciate. The differential transport characteristics of the loop of Henle. We're reabsorbing water on the way down, salts on the way up. Generates concentration gradient in the medulla. The vasa recta then uses these concentration gradients, remember the vasa recta is a capillary bed, to recirculate salts and urea in the medulla. Then you've got a concentrated medulla all ready to go, and then you can save water and concentrate the urine with the help of ADH and do it quite rapidly. Alrighty. ADH is released from the posterior pituitary. So if you remember, this is the hypothalamus. You're going to have some neurons up here. They're going to have long axons that go down to the posterior pituitary, and that releases ADH. Some people call this vasopressin because it contracts blood vessels. But I like to call it ADH, which stands for anti-diuretic hormone. So, released from the posterior pituitary, but made in the hypothalamus. And we think in the hypothalamus there are osmoreceptors. Receptors. And that when extracellular fluid osmolarity increases, the osmoreceptors shrink, which stimulates these cells. Then these cells have action potentials, and ADH is released into the blood. ADH goes to the collecting duct and increases water permeability, and it does that through the upregulation of aquaporins. Then the collecting duct reabsorbs water, and then less water goes out in the urine. So you produce less urine and save more water, and the urine that you produce is very high in concentration. So that ADH, and here we see vasopressin. Vasopressin and ADH are the same peptide. Vasopressin binds to its receptor. This is a G protein coupled receptor. So we activate adenylyl cyclase. Cyclic AMP through protein kinase A phosphorylates proteins, and we have vesicles of a certain kind of aquaporin, aquaporin 2, that gets inserted into the membrane, and now there's a way for water to cross the cell. There are aquaporins over on this side, but these guys are here all the time. These are not the ones regulated by ADH, and the ones in the loop of Henle are not the ones regulated by ADH. So if we're removing water, then salts are left behind, and the urine gets more concentrated as we save the water. Now, does ADH mean you don't have to drink water? No. You have to make some urine with some water in it. So everybody has something called an obligate water loss. An obligate water loss. What in the heck does that mean? That means that if you make, oh geez, let's see. If you make let's say, 500 or 600 milliosmoles of waste, uric acid and creatinine and urea and all these waste products, and you have to get rid of them. And you can only make your urine so concentrated. Remember? If you look here, we can only go to like 1200 or 1400 milliosmolar. So let's say if we make 600 milliosmoles of waste per day, and we can only make the urine up to 1200 milliosmolars per mil, per liter, then it means we have to make 0.5 liters per day. So humans have to drink water. There are some little desert animals that can just take a little bite out of a cactus, and they don't even really need to drink water because they're able to make their urine so concentrated. But we are not desert animals, human beings. We are not. We have to have access to water. So we have to drink at least a half a liter of water a day to maintain our osmolarity. But while we're trying to get access to water, ADH will save our life and help us hang on to water. Now, everybody's running around with their Camelback little bottles and they're drinking water all day long. Do people need to drink that much water all the time? I don't really think so. But you do have to drink some. in order to maintain water balance. You can't just go around not drinking water at all. So you do need to drink some water. Do you need to drink 14 bottles a day? I don't really think so. Because this ADH mechanism. So ADH is a negative feedback mechanism. I mean, how is it a negative feedback? Well, our water or our plasma, whatever, should be about 300 milliosmolar. Osmolar. Let's say your osmolarity goes up to 310. That means your osmoreceptors will shrink. You'll produce ADH, you'll try to save water, and get your osmolarity back to where it should be. ADH will also stimulate your thirst. Angiotensin II will also stimulate your thirst. You'll try to drink water too. If your osmolarity should be 290, 300, and it should be 300, let's say it goes down to 290, you're going to turn ADH off because you don't need to be saving any more water. There are situations where it's usually people with psychological issues who will drink and drink and drink and drink and drink water. They will make themselves so dilute that ADH, they've been totally inhibited ADH and they're still drinking water, and they get hyponatremic and they can have a seizure. There are other folks that cannot make ADH. They are not able to make ADH, and they have something called diabetes insipidus. They cannot make ADH, so they cannot concentrate the urine. So they have to drink a lot of water. This is a disease that was called in the old days the pissing evil, which I think is hysterically funny. So you have to drink a lot of water. There are also other people that have maybe a brain condition, maybe they have a tumor or something, and they're making more ADH than they need to. That's the syndrome of inappropriate ADH secretion. So these folks concentrate the urine too well. So instead of drinking water, these folks need to limit their water intake. So that they don't become hyponatremic. I'm thinking I'm going to stop here. So I think I'm going to stop this presentation, and in the next one we'll talk more about the distal nephron and about fluid and electrolyte balance. So thanks for listening, and I'll see you next time.